At midnight, UTC, the world's clocks gained 1 extra second, and Reddit, LinkedIn, and half the airlines on Earth fell over. June 30th, 2012. Within seconds of that clock rolling over, server dashboards around the world lit up red. CPU usage didn't climb. It slammed straight to 100% and stayed there. Reddit went down. LinkedIn went down. Mozilla, Yelp, Foursquare, StumbleUpon, all hit. And at airport check-in desks in Australia, the computers simply stopped. Qantas and Virgin Australia staff had to check in passengers by hand, on paper, for over an hour. Nobody had deployed new code. Nobody was attacked. Every one of these machines was brought to its knees by the same thing: a single extra second that everyone knew was coming. To understand what happened, you need to know why that extra second exists in the first place. We keep time two different ways. Atomic clocks tick with almost perfect regularity. That's the time your computer trusts. But the actual length of a day, one spin of the Earth, is slightly irregular and slowly getting longer. Over time, these two clocks drift apart. So a few times a decade, the world's timekeepers force them back into sync by inserting 1 extra second, a leap second, into the last minute of the day. That minute has 61 seconds, 23:59, and 60. On the surface, handling this is trivial. Once in a while, the operating system's clock is told, "This minute, count one more." So on June 30th, 2012, at midnight UTC, Linux machines all over the world did exactly that. They inserted the leap second. And then they caught fire. Not literally, but the load graphs looked like it. So if inserting 1 second is such a simple operation, why did it detonate? Here's the strange part. The engineers who logged into these servers didn't find crashes. The machines were up. They were responsive-ish. They were just completely pegged, burning 100% CPU doing nothing useful. To see why, you need to know how software waits. Programs constantly set tiny timers. Wake me up in 10 milliseconds. A web server might set millions of these a second. The kernel keeps a list of them and fires each one when its moment arrives. Normally, this is a calm, orderly process. A timer fires, the program does its work, and if it's a repeating timer, it rearms itself for the next round. Fire, rearm. Fire, rearm. Forever, but gently. Now watch what the leap second did. When the kernel inserted that extra second, it changed the system's idea of what time it was, but it forgot to tell the timers. Every one of those pending timers compared its wake-up moment against a clock that had just jumped. And suddenly, timers that were supposed to fire in the future looked like they were already overdue. All of them, at once. So the kernel did what it's supposed to do. It fired them. All of them, immediately. And each repeating timer, the instant it fired, rearmed itself and was instantly overdue again. So it fired again, and rearmed, and fired, and rearmed, and fired. This is called a livelock. It's the evil twin of a crash. A crashed program stops. A livelock program never stops. It spins forever, doing real work at full speed. Work that accomplishes absolutely nothing. From the outside, the CPU looks maxed out and busy. From the inside, it's a dog chasing its own tail 1,000,000 times a second. Multiply that across every core on every affected server, at Reddit, at LinkedIn, inside the airline reservation systems, and you get a global outage triggered by a single tick of the clock. The engineers scrambling that night didn't have time to wait for an official kernel patch, but someone discovered something, almost insulting in its simplicity. You didn't need to fix the code. You just needed to set the clock again. Running one command that reset the system time, or, in a pinch, just rebooting, snapped the timers back into agreement with the clock, and the loop stopped dead. Whole data centers were rescued that night by the software equivalent of turning it off and on again. But that was a bandage. The real bug was 5 years old, and it was hiding in a line of code someone had deleted. When kernel developers traced the fault, the story got stranger. This wasn't a bug in the 2012 leap second code. The trigger was a missing safeguard, and it had been missing since 2007. Deep in the Linux kernel, there's a function whose entire job is to announce, "The clock has changed. Everyone recheck your assumptions." It's called whenever the time is set. And back in 2007, during an unrelated cleanup, the call that fired it during a leap second was quietly removed. It looked redundant. It compiled. Everything worked. For 5 years, nothing happened. Because the only thing that could expose the gap was a leap second, and there wasn't one. The bug sat dormant in millions of machines, waiting for the Earth's rotation to hand it a trigger. You'd think the fix is obvious. Just put the line back. And in essence, that's what happened. The leap second code was changed to announce the clock update again. But there was a catch, and it makes this a great little lesson in systems design. That the clock changed work has to happen on every CPU core independently. Each core keeps its own set of timers, and it can't safely be done in the exact moment the leap second is applied, because that moment runs in a special, locked-down context where heavy work isn't allowed. So the real fix was subtler than the bug. Detect that you're in that restricted moment and defer the announcement. Hand it off to be done safely on every core a fraction of a second later. Fix the desync without freezing the very thing that inserted the second. Step back and you can see the shape of it. A perfectly ordinary line of code, removed because it looked useless. A trigger so rare it only appears a few times a decade. And a whole class of software, anything that waits in tiny increments, sitting directly in the blast radius. None of these was a disaster alone. Stacked together, they took down the front page of the internet. In the days after, patches went out fast. Red Hat, Ubuntu, and the rest shipped fixes. Sysadmins who'd been paged at 1 a.m. compared notes on exactly which command had saved them. But the deeper reaction was philosophical. A lot of engineers looked at the chaos 1 second had caused and asked a simple question: why are we doing this at all? Google had already seen it coming and used a clever trick called a leap smear. Instead of one jarring extra second, they spread it across the whole day, adding a few invisible milliseconds at a time, so their clocks never had to count to 61. That debate never fully ended. The leap second was so disruptive, so universally hated by the people who run computers, that in the years since, the world's timekeepers voted to phase it out entirely. One of the biggest changes to how humanity keeps time, driven, in no small part, by nights like this one. 1 extra second did all of this, which raises a darker question. What happens when the clock doesn't gain a second, but runs out of them completely? Because there's a moment, already scheduled, when a huge chunk of the world's computers will hit a number they physically cannot count past. It's called the year 2038 problem, and it's on the screen right now.